Hello, and welcome to our presentation of Dreaming Up Metamorphic Relations, Experiences from Three Fuzzer Tools. My name is Andrei Lasco, and I will present the first half of this talk, while my colleague, Matt Twinzer, will be with you for the second half. In this presentation, we first briefly discuss metamorphic relations, or MRs, and give a short background of each of three tools we will reference in this work. We then describe our three main categories of sources of inspiration, providing some personal examples of how they each helped us generate MRs during development of our tools. We finalize with a few words about the future of the three projects and what we learned from each other during the process of discussing MR generation. Metamorphic testing is only as effective as the MRs used to employ it. And generating these MRs is a difficult problem, especially selecting effective MRs for the specific system under test in order to maximize testing efficiency. Suppose you want to test an implementation of sine. Testing whether sine of x is equal to sine of x plus 2 pi is a good MR. For testing sets, you can check whether a set intersected with the universe set yields the original set. But what about programming languages, compilers, SMT solvers, and more? As inspiration to generating MRs, we distinguish three main categories. Specifications for the system under test, such as existing documentation, for example programs using the system under test, or the associated test suite for that system. Second, prior work done applicable to the system under test, which can be existing testing tools either applied or portable to the domain of the system for expert knowledge by developers or maintainers. Finally, using additional metrics to guide the process of deriving additional MRs, such as code coverage or text-based searching. As can be seen in the figure, all these elements are interconnected, such as experts writing the documentation of a system. Our three tools have all been developed independent from one another, but the processes by which we came up with MRs for each tool are relatable. A few words about each tool. MF++ focuses on testing correctness of C++ software libraries by composing small, user-provided equivalent implementations of high-level operations together to randomly produce rich equivalent MRs. Applying these MRs over some given input should yield equivalent output, divergence pointing to potential bugs. C4 focuses on testing whether C compilers implement atomic action concurrency correctly. It does so by applying semantics refining transformations to litmus tests, which are self-contained concurrency tests with a known input and a postcondition over the possible non-deterministic outputs. spirv-fuzz finds bugs in compilers for SPIR-V, an intermediate representation for graphics programming, by applying semantics preserving transformations to an input spirv program. The original and transformed program should lead to the same image being rendered by the graphics pipeline. If different images are observed, this points to a bug in the spirv compiler for the device under test. The first, and probably obvious, source of inspiration we consider is the specification of the system under test. This includes any official documentation prepared by the developers of the system under test, provided test suites and example programs, as well as the source code itself. The latter includes header files, reasoning about the code itself relative to the expected semantics, and any additional inline documentation that might not be part of the official documentation, potentially contained within comments, for example. Basically, anything contained within the system falls in this category. For example, spirv allows for certain attributes to be provided to calls, which should only provide hints or requests that the compiler acts in a certain fashion if possible, but should have no observable effect otherwise. Adding such attributes is a simple MR, which should maintain observable equivalence, something that spirv-fuzz is aiming to achieve. In one particular instance, adding a don't inline attribute, which requests that the corresponding function is not inlined, triggered a miscompilation in Swift Shader, a software renderer. Another source of inspiration is prior work. If metamorphic testing has been applied in the domain of the system under test, we could attempt the MRs used in that experiment over the particular system we would like to test. Alternatively, we could port compatible MRs from another domain, such as multiplication by 1 in the integer domain, becoming a conjunction with truth in the Boolean algebra domain. We could look at previously solved bugs or discussions related to potential edge cases or under-tested features, and try to extract MRs from the ensuing back and forth. Or we could directly ask the developers about features of interest of the system under test to be exercised, potential usage examples, which can then be integrated in the testing tool itself. MF++ started as a project devoted to testing the integer set library, or ISL. Discussing with developers of ISL, we were advised that the coalesce operation was a very useful internal optimization done by ISL. Coalescing is essentially a heuristic which optimizes how a set is organized internally, and, as can be seen in the code on the left, applying it requires certain conditions be met. As this is an important albeit under-tested optimization of ISL, it was a good candidate to apply MF++ to. However, understanding the code is particularly difficult, and we relied on the expertise of ISL developers to present this operation in an understandable way. As can be seen on the right, each condition refers to the input having certain geometrical shapes. Thus, we were able to enhance our testing and discovered 3 bugs related to this operation. My colleague, Matt Windsor, will now talk about inspiration from metrics.
Okay, so I'm going to be talking about inspiration from metrics, and the 2 types of metrics that we focused on in our experience report were code coverage, specifically of the metamorphic relations against the system under test, and also the textual analysis angle, which would be focusing on the text of the source code of the system under test. And these 2 metrics complement each other quite well. We can use the textual analysis, for instance, to hone in on pieces of the system under test for which it would be useful to do a full code coverage experiment. But also they interact well with the previous strategies that we underlined earlier on in the talk. For instance, in the prior work field, domain experts' knowledge can really help us understand how to create and also interpret metrics on systems, especially ones for which we are not very familiar. And also, they help us focus the reading of the source code of the system under test and other forms of specification. So when we're looking at inspiration from metrics, we may be wanting to ask and answer 2 key questions. Firstly, how well do our existing metamorphic relations capture the system under test? It may well be that the metrics show that the metamorphic relations do a good job of capturing the system under test, and maybe we can use that to work out other metamorphic relations that would do a similarly good job, or maybe we have enough metamorphic relations in that area. Alternatively, we might find that they do not capture the system under test very well, or that there are areas for improvement. And that factors into the second question, whether there are specific parts of the system under test that new metamorphic relations, hopefully guided by the metrics themselves, would help us to capture. So, giving a brief outline of metrics, I'm now going to go into a worked example from C4. Now, C4 targets compilers such as LLVM and the GNU compiler collection, and these are notoriously huge systems under test. They implement a very large amount of features of a large amount of programming languages, not just C, but also possibly C++, Fortran, Ada, and other such languages. And they do so for a great deal of processor architectures. And this is an issue for C4 because C4 is actually honing in on a very specific subset of this search space. So it's specifically looking at atomic action concurrency, which is a fairly small feature nestled inside the compiler. It's focusing on C11, only 1 language, and it's focusing on a small handful of architectures that we were able to run experiments on easily. And this means that if we want to understand the system under test from the point of view of what's important for C4 and what would be good for devising new metamorphic relations for C4, we have to really cut down and focus in on the specific part of the system under test that is interesting. And this is where metrics come in handy. The main metric that we used for this particular requirement was textual analysis, and we actually do a fairly basic but quite effective form of textual analysis where we quite literally search the source code for keywords such as atomic. And it turns out that even the word atomic is useful for finding code that works with atomic actions. For instance, this example here on the slide is one where we looked for the word atomic and found what looks like a small casting operation in the middle of a large wad of code, but is in actual fact part of a optimization that targets atomic compare exchange instructions. And by finding this, we were able to tweak our metamorphic relations that created compare exchanges, both to try to exercise this particular optimization and also to produce compare exchanges that deliberately would not be optimized by this particular optimization. And that's attempting to cover the bit of this optimization that is guarding against things where it is unsound to optimize in this way. And doing this textual analysis also helps with coverage, which in turn is useful for understanding how well C4's metamorphic relations capture the specific parts of the compiler we're interested in. So trying to get coverage on the entire compiler would not tell us a lot, because there is a large amount of the compiler that has nothing to do with atomic action concurrency. Okay, so that is inspiration from metrics, and that actually wraps up the talk itself. In this talk and in the experience report itself, we have outlined a loose framework for understanding the sources of inspiration that we found useful when devising our metamorphic relations using tools. So the metamorphic relation categories we've looked at are specifications, prior work, and metrics, and these have proved useful for categorizing our experiences with MF++, spirv-fuzz, and C4, and those tools are free and open source software available at the respective GitHub links on the left-hand side of the slide. And what we've really tried to do here is, we haven't tried to create a formal taxonomy yet, but we feel like our work might be the start of a conversation that could lead to one. And indeed, we hope that our work has been useful for practitioners creating their own tools to understand the space of possible sources of inspiration, understand where they get their inspiration from metamorphic relations from, and hopefully open conversations where we can inspire each other to do more interesting things with dreaming up metamorphic relations, and also hopefully to dream together to find these metamorphic relations in future. So thank you very much for your attention. We would be happy to take any questions, provided that there is time available.
And well, hello again. Welcome to the last Q&A slot of the paper Dreaming Up Metamorphic Relations Experiences from 3 Fuzzer Tools, the winner of the Best Paper Award. We are lucky to have here with us Matt Windsor, Andre Lascu, and Alastair Donaldson, that will be more than happy to take your questions. So please go away, ask your questions on the chat, please. We already have the first one from Megan. Thank you, Megan. Have you considered putting together a website or similar to add as a repository of metamorphic testing approaches, perhaps following the taxonomy? Maybe this type of repository could also help spread knowledge of metamorphic testing. Matt, would you like to answer?
Sure. So, as we said at the end of the paper, really what we're feeling with regards to our paper and our work is that it's really the start of a conversation, and we had quite a lot of examples in a loose taxonomy following strategies, but there certainly would need to be a lot more conversations to try and build up a formal repository of approaches. Certainly, we hope that there would be approaches that can be gleaned from the examples that we give, and a website does sound like it would be a really nice go-to for learning more about metamorphic testing. Certainly, I think that there would need to be a lot more conversation and formalization between now and then. But thanks for the question.
Okay.
Does anybody else have any?
If I might just follow up slightly on that. just want to mention that there was a paper actually at the first Metamorphic testing workshop called Looking for an MR, Ask MetWiki Today. And there was a website called MetWiki, which I believe has a bunch of examples of MRs. Yeah, so I don't know what the latest is with that. I'm having a look at it right now as we speak.
Okay. Perhaps you could write the link in the chat, Alistair, if you have it.
Yeah, sure.
Yeah, great. Okay. Well, in the meantime, while people far away, I would like to ask a question. I think this is something that you have considered at some point. I would like to know your opinion after all this time, after your whole experience. Have you considered using metamorphic relation for detecting performance bugs? That's something I think that you consider at some point. Do you think it could work based on your current experience? Andre, for example, would you like to answer?
So just to double check that you said performance, right?
Yeah.
Yes. So actually, I have heavily considered investigating performance. I actually even took a couple of months to inspecting how useful this is in the domain of SMT solvers. And I think the outcome of that work was, at least for SMT solvers, it was very hard to see what was a bug that might have mattered for those developers, or something that's just an outcome of the fact that they're heuristic-based tools and solving very hard problems, and there's really not much you can do to improve them. So I think maybe if you're a domain expert, it definitely is possible, but the metrics, you need to very clearly know what metrics to target. You need to understand what something is actually something of interest and not just a matter of a circumstance. So yeah, I think it might be just a hard problem, but very possible.
Okay.
We used fuzzing in our work, and I think something we discussed, Andrew, if I remember rightly, was that combining metamorphic testing with fuzzing, well, that could be great for finding bugs, functional bugs. For performance bugs, it doesn't work so well because the fuzzing tends to create quite pathological examples, which may be great for revealing a bug that you could then simplify to a non-pathological bug triggering example. But I think if you, say, massively inflate an SMT formula like we do in Andre's work that we describe in this paper, then you may just get an SMT formula that is way harder to solve, so it takes longer to solve it, and that's not a performance bug. So yeah, I think to use metamorphic testing for performance bug finding, I think you have to have, I guess this is kind of what you were saying, Andrew, you have to have an expectation that applying this MR should either not change the performance of the SUT, or it should have an expected outcome, like it should make the SUT, say, perform faster. So if you see it go slower, then that looks like a bug. I think in our domains, we don't really have an idea about getting a handle on that.
Okay, I see. Yes, I agree that it's quite difficult. There's another question. Melvin says this is a vague question, but they wonder about code coverage. Just how useful is this metric for assessing metamorphic relation quality? I'm not sure how on topic the question is, though. Matt, would you like to answer the questions?
Sure. So code coverage, yes, that's something that we talk about in the paper, but on the flip side, which is, I think, using code coverage as a way of finding ideas for metamorphic relations. But it certainly, one thing for C4 at least, I don't know how well this generalizes, but one thing that we were looking at with C4 was specifically if we're using certain metamorphic relations to apply transformations to a C program, we'd ideally like to see an increase in the code coverage of the compiler. And that's certainly, I think, specifically for our example, that's quite useful because what we are wanting to do is we are wanting to try to exercise as much of the compiler as possible with the metamorphic relations. But I get the feeling that that is quite specifically tied to the domain that we're looking at in C4. I don't know if if Andre and Alistair have any sort of inputs with regards to spirv-fuzz and MF++.
Personally, on my side, I think quantifying the quality of an MR from code coverage, it depends what you're aiming to achieve. If you're just aiming to have a system that, like a MT tool, which tries to test as much of the program as possible, and as much of the program can be quantified via code coverage, then yes, that. But you might have a very interesting MR that touches very few parts of the code, but those parts of the code are on the critical path of the SUT. So I think I'm not sure how to assess the quality of an MR from the achieved code coverage.
I think it's a really interesting question, Melvin, and I don't think it's vague at all. And the thing is that if you think coverage is a good proxy for bugs, then I think it's a good metric, because people tend to be impressed with MRs to find bugs. Now, if a system is bug-free, then you'd say no MRs are any good, right? Because you wouldn't find any bugs. And you're not going to find bugs if you don't cover code that has bugs. So coverage certainly is got some value as a measure of MR quality. The trouble is you may vacuously cover code. You may cover code in rather meaningless, uninteresting ways thanks to MRs. Something Andrea and I are interested in is if you generate a follow-up test case using an MR, and that test case covers code that you couldn't cover in your existing test suite, then you now have a test with an oracle, thanks to the MR, that does give you improved test suite coverage, and that seems worthwhile.
Okay, there's time for a very fast final question. Actually, I had this myself as well. Did you find that one source of inspiration is either more used or more effective than others? You know, that will help to prioritize. I mean, if I only have time for one of those, which one should I pick?
Let's do one per tool. spirv-fuzz, reading the specification carefully. That's the best source.
Okay,
What
great.
Or C format.
Well, we have 25 seconds left. So thank you so much, guys. I would like to thank the speaker, thank the participant. Now we are going to the closing, but I would like to thank these speakers for the nice presentation, the nice work, and also for the Best Paper Award. Remember, we have here with us the winners. Congratulations. And that's it. Thank you very much.